Hi, my name is Jeff, and today I'm going to show you the digitization process of these old phonographic cylinders. We'll be using the endpoint machine, which is a state-of-the-art combination of analog and digital technologies, along with a digital microscope. And it will allow us to calibrate and compensate for certain deficiencies that you find in these ancient old cylinders.
Tell us about different kinds of cylinders.
Many of the cylinders that we have in our collection were mass-produced. This one is by Thomas Edison. He had a record company. And they're familiar melodies that everybody knows. These were mass-produced. But today, I've chosen to digitize this brown wax cylinder. These are the most interesting in the collection for me because these were actually homemade. You could buy a machine, take it home, take a blank brown wax cylinder and record whatever you want. So generally the content that you find on these things are either field recordings or it's just some family at home having fun. And since these were never mass produced, these are original master recordings, and it's likely that nobody's heard these for the past 110, 120 years. So today we're going to discover what's on this.
Show us how you set up the endpoint.
Now, one of the coolest features about the endpoint machine is it has an optical laser that will allow us to actually preview the disc without having any physical contact with it. So we're going to do that right now. So right now we're hearing just the laser. And if you look closely, you can see how the mandrel is warped. That's because the cylinder itself, over these years, has become distorted. So we can hear that there's a voice on there. Before we do the actual encoding process, we're going to calibrate it so that the cylinder is balanced out. And we do that using the laser technology. We're going to measure the distance from the laser to the cylinder at varying points on the cylinder and then calibrate it so that that distance is identical. It's called the mandrel set process. It starts with a measurement, a comparison, and then an adjustment. You can see here on the screen, it's telling us that we have to adjust it within micrometers. Very, very small amounts. So measure, compare, and adjust. We do this at several points. Okay, so now we are going to record this using the stylus. The stylus and the mechanical pickup is always the best quality audio. And now that we've calibrated the mandrel, you can see that all of the warpage has been compensated for, and we're looking at a completely flat cylinder now. It's very important that we have all of the correct information encoded into the audio file itself using metadata. And this will include things like the type of machine, the type of needle, the type of stylus, the preamp that we're using. We'll be recording at 96 kilohertz, 24 bits. So all of this information will be included in the audio file itself. Now, 96 to 24 is not the highest bit depth and sample rate currently available, but according to industry standards, that this is a sufficient representation that if there's any technology in the future that's developed, that this will encode these cylinders at a high enough resolution so that the people in the future won't have to go back to the original carrier. We're using Wavelabs to encode. Even though these cylinders are monophonic, we're going to be using a stereo stylus. And the reason is because we want to capture both sides of the groove. I have this one wired in what's called a vertical configuration, which means that the left and the right side are 180 degrees out of phase from each other. And the reason we do that is because any noise and crackling and popping that exists on this cylinder, when we reverse that phase later on, it's going to be our first stage of noise reduction. So, we're going to record this now using the stylus. And here we go. And you can see here on the endpoint machine, it's giving me information about exactly how warped the cylinder is. Other information about the lasers and everything that we have is represented here.
What is the post process and why do you do it?
We're going to go to our software. So, as I said earlier, the left side and the right side are 180 degrees out of phase. So that means that whatever content is common right now is going to be phase canceled. So that voice that we heard is going to be almost inaudible. We're going to hear mostly noise. But listen to what happens when I reverse the phase on one side. The common thing, which is the voice, goes into phase, it becomes reinforced, and all the other noise is now out of phase, which then gets canceled out. And then at this point, we're going to sum both channels together and create a mono file. And we're going to export that and call it a master copy. A master copy is going to be our archival copy. It won't have any noise reduction aside from the phase cancellation that I just showed you. And this will be the unchanged version that will go into the future. We'll be saving every a version of the recording along the way in case there's some engineer in the future or some new kind of technology that exists and they want to go back to the original recording, they can. But our working copy is called the master copy. So now we're going to open our master copy in another program. It's called iZotope. iZotope is great for its noise reduction, pop reduction, and other mastering features. So if you look here, you can see things like this. This is a pop. This comes from possibly a damaged section. So first thing we're going to do is we're going to remove those. So we have a plugin here called declick. And by setting it up to preview, we can hear what it thinks is clicks. And once we've found those, we're going to remove them. And then you can see on the waveform how all of those clicks are then removed. We're going to do a few stages of this. And we're going to switch the view here to the spectrogram. Spectrogram is represented by frequencies on the up and down axis. Time is left to right. And then the brightness of the object is amplitude. So you can see where the actual music is. And then in this case, we can also see where the noise is. So this is the noise we want to remove. So first thing we're going to do is we're going to sample that and then instruct the computer to look for any examples of that and then remove them within the actual content. So we're going to preview. It's a plugin called Spectral Denoise. So we're actually listening through the section of the song, and we can hear, even though there are vocals on this, we can't hear them. It's just noise. So we know now that it has successfully recognized what is noise. So now we can remove it. And so now what we're going to hear is a ghost from 115 years ago, and we are most likely the first people to hear it in that amount of time. Here it is. Now, last process, using our digital microscope, we're just going to capture some physical evidence of what the actual condition of the cylinder is in. This one is actually in pretty good condition. It doesn't have any kind of physical damage or mold, which can be very common in some of these. So we take a photo of the beginning, the middle, and the end. Here at the end you can see there is a little bit of a scratch and a gouge. I didn't notice that on the recording. And then we are appending the same naming mechanism that we have for the audio file to these photograph files as well.
What have been your favorite discoveries?
What I find fascinating about this is it's just a solo male voice. And I try to imagine what the situation was. He was just sitting alone in his home one day. Maybe he was drinking Slivovitsa. And we're hearing a ghost. And because this was not a mass-produced cylinder, there isn't a lot of information. But this was handwritten on the lid. Can you see that? So we don't know who this person was. A voice from the past. Okay, so we're going to compare the original unprocessed audio with the final audio with noise reduction. This is the original. And this is our final audio product. And then we have a complete digitization of whoever this gentleman was. And that's it.